Number 22. Under certain conditions, the decomposition of ammonia on a metal surface gives the following data. And then they give us this beautiful little table here. And from this information, we have to find out or determine the rate law, the rate constant, and the overall order for this reaction. Fun times! But it'll be fun, right? Hanging out with me, right? But we'll get it down. So the key thing here is that whenever you have a chart like this and they're asking you for the rate law, this is a very standardized type of question. So whenever I see a chart and they're asking for the rate law, it's always basically you're going to be doing one thing. And they're describing that they want you to find the rate law, but secretly they want you to find something else, or the question wants you to find something else. Whenever they're asking for the rate law and they give you a chart, we always have to find the orders of the reaction. Now, what do I mean by the orders? Well, if we look at a general rate law formula, which is this, right? If we look at a general rate law formula, we know that it's rate equals K, and the K value is the rate constant. So that's going to be coming up. We have to find that out. So it's rate equals K times the concentration of the reactants. Anytime that there's brackets here, that means concentration, molarity. And it's raised to those orders. So if we want to find the order, the thing that we just have to basically find is the exponents. All right, pretty simple enough. We got this. Now, the easiest way that I find to do this is that we definitely have to use a type of ratio where we're going to be putting one rate law over another because they gave us 3 separate trials or experiments. For one trial, they gave us a molarity value for ammonia, and just know that NH3 is ammonia. And for a certain molarity, out comes the certain rate for that reaction, how fast the ammonia is decomposing. They give us a second molarity value, and the rate is, dictating how fast the ammonia is decomposing. So in this case, we have 3 trials, or if you want to call them experiments, that's fine as well. So we have trial 1, trial 2, and trial 3. Now, the easiest way to go about this is to always put the higher rate value. So you're looking for a higher rate and you want to divide by the lower rate. It just makes the math easier because you'll be dealing with whole numbers or, greater than 1 numbers and not fractions. But if I look here at all my rates, they're all the same. 1.5 times 10 to the negative 6, 1.5 times 10 to the negative 6, 1.5 times 10 to the negative 6. So there's really no higher or lower rate. So instead of going by higher and lower rate, for this one, we could go by higher and lower concentration of NH3. And that's where you have the changing numbers. And it doesn't really matter which one we choose. Whichever choice you want to use, whether we're going to go trial 2 to trial 1, or trial 3 to trial 2, or trial 3 to trial 1, you'll still get the same answer. So if you want, you can, as I work through one of the 2 trials that I'm going to pick, you could try a different one and see if the answer matches with mine. So in this case, let's see, I'm going to pick trial 2 over trial 1. So I'm going with that higher rate, dividing by the lower rate. You could do 3 to 2 or 3 to 1 and see if you get the same answer. So we're going to do trial 2 divided by trial 1. And what that means is that I'm going to plug in the whole rate general law that I can for trial 2 and divide it by the whole rate law for trial 1. So for trial 2, the rate that was given, is the 1.5 times 10 to the negative 6th. And this equals a rate constant value, but they didn't give it to us, right? And we have to find it after we find the rate law. So I'm just going to leave it as K. And this is going to be times by the concentration of the NH3. So in this case, it's going to be 2.0 times 10 to the negative third, and that's going to be raised to its order. Now remember, we're trying to find that order, so I don't know what it is. So I'm just going to label it for now as x. You could choose any value. Doesn't really matter. And I'm going to divide all this by, we're going to do it again for the trial 1 values. So the trial 1 rate was 1.5 times 10 to the negative 6 equals the rate constant, still don't know that, okay? And now the trial 1 concentration was 1.0 times 10 to the negative third. And since it's the same reactant, it's the same NH3, you've got to raise it to the same exponent. So if you call this x, you got to call this one x. And now we just take this and we try to simplify as much as we can. And it's a beautiful thing because even though we don't know the rate constant, it's technically the same number. It's a constant number. So k divided by k, can we say bye-bye? Get rid of the k's. And anything else that we can simplify, right? 1.5 times 10 to the negative 6th divided by that same number. What do you think? I'll give you a little bit as I try to color this in. Do you know it? 1.5 times 10 to the negative 6 divided by 1.5 times 10 to the negative 6. You got it. It's just 1. So 1 equals, right? This cancels out as well. And now we need to do 2.0 times 10 to the negative 3 divided by 1.0 times 10 to the negative 3. We can just use the calci. I mean, this is going to come out to being 2. If you have the same exponents, don't even worry about those. Just do this math. So 2 divided by 1 is 2. But I have the calci here, so I feel like I have to use it. So 2 times 10 to the negative 3 divided by 1.0 times 10 to the negative 3. And there you go. So we got 2. And now the exponent just comes along for the ride. X. Beautiful. So now we have this dilemma. We have to say to ourselves, 2 to the what will get me 1? Now this is a very specific exponent rule here, right? Because if I do 2 to a number, I will get 1. If I do 3 to that same number, I'll get 1. If I get 4 to that number, I get 1. Do we know what that x value is? Yeah, you got it. 2 to the 0. So even if I have a decimal, right, 0.56 to the 0, that's going to equal 1 as well. So any number that you have, if it's equal to 1, it's always going to be 0. The only one that's the different one is whether you do 1 to the first, that could equal 1, or if you do 1 to the 0, that also equals 1. So, but all the other ones will equal 1. So we know that the order here is x equals a big fat 0. So let's now go back and answer the question. They wanted the rate law, which means that the only number that you have to plug in is that exponent, is the order. So I'm going to leave it as rate equals k times the concentration of the reactant. We only had one reactant, NH3, raised to its order. We found out that the order was equal to 0. But remember what we just talked about. Anything raised to the 0 is 1. So essentially, it's just going to be k times 1. So you can say bye-bye to this. And now we have a more specific rate law. The rate law is just rate equals k. And for this one, that's totally a-okay, because sometimes that can happen. So for this, the rate law is just equal rate equals k. That's it. Now, we're going to use this information to solve for the next piece of the puzzle. The next piece of the puzzle that they wanted was the rate constant. So now, we're going to find the rate constant. And just like we said before, the rate constant is the k value. Now in this case, since we have the rate law, rate equals k, maybe I'll make it red, It doesn't really matter what trial you use. You got to pick one trial. I guess, just to kind of show you that you can mix and match, I use trial 1 and 2 to find the rate law, so I'll use trial 3. But it does not matter. So trial 3 says, well, whatever that rate was. And do you see how, if whatever trial we used in this case, the rate's going to be the same, because it's the same number. So 1.5 times 10 to the negative 6th. And now just include those units. The units for the rate was mole, liter to the minus 1, which means it's just in the denominator, and hour to the minus 1. So H and hour, HR, is the same thing, and that equals to K. We didn't even have to do any math here, which is beautiful. And that is the rate constant value. The last thing we have to do is find the overall order. Now, overall, not the overalls that you wear. Oh, what was that? I don't know, but we're going to keep going. The non-overalls, the overall formula, that just means that it's just the sum. So what you're going to do is you're going to add up all the orders, all the ones that we have in our formula. But for our rate law, right, there was only just one number, and it was 0. So in this case, you don't have to add it up because you only have one order. So the overall order, in this case, is just the 0. Whoa, that's pretty cool, though. And that's the answer here. And we are done with this problem. Pretty long steps, but it's well worth it in the end. Once you get all of it, you're like, look how beautiful this is. Sometimes I look back and I'm like, wow, that's nice. That's colorful. And you guys know how particular I am. If you guys have been with me in the beginning, since the beginning, which, by the way, thank you so much for your support. And I really hope that this is helping you out. But if you guys have been here in the beginning, you know that I'm very picky with how it looks on the screen. So that's just me being me. But anyway, thank you so much. I hope this helped. If it did, and you want us to have the potential to reach more people, please hit the subscribe button. It takes a couple of seconds, and by you making a difference in your day for just 1 second, just a single click will make a huge impact in ours. My brother and I, we really do appreciate you guys so much. Thank you so much for all your kind support. You guys rock. I mean, there's no other way to put it. Thank you so much. You guys are greatly appreciated, and I hope to be talking to you in future lessons, all right? Check the channel out. We got thousands of videos for you guys, so always keep learning. I'll talk to you soon, okay? All right, bye-bye.